6.4, work. We have our notes, we're on page 17. Work. We were just talking about work. This class takes a lot of work. Work is actually a measurement in math and physics. It's actually more of a physics thing. We're going to talk about the calculus behind some of the physics of work. So we use the word work all the time. You know, I went to work today, I'm at work right now. You did a lot of homework. Work mathematically is defined to be how much, how do I say it? It's defined to be how much work you do in moving some certain object, say, with a certain amount of force, a certain distance. For example, if I want to take this tissue box and set it on this desk if it was clean, and push it across from here to there, with just my one little finger, I could probably do that no problem if the paper is out of the way, right? It would slide real easy, doesn't weigh much. So that wouldn't take much work for me to slide it across the table. This water bottle right here is full. I don't know how much it weighs, but I dropped one on my toe over the holidays, and I think my toe's still broken. But if I wanted to set this on the table and push it with one finger across the desk, I probably could get it over there. But do you agree I'd probably have to push it a little bit harder than the tissue box? It'll take more work to move this across there, because it's heavy, than it will to push this across there. So it's how much force do you need to move something a certain distance? Or maybe it's lifting. If I want to lift this from here up to the top of the ceiling, it's not too hard to lift. Don't even feel it in my little arm muscles. But to lift it up to here, a little bit more work. My little biceps are straining. So it's more work to lift it. So it's force times the distance. It takes more force to do that water bottle than the tissue box. Okay, so it's defined to be, up there at the top of your page, force times distance. Force times distance. How much force, how much distance. And depending on whether you're working in the British or American system or the international system, our units are different. You already know that a little bit, you know, like if you want to go buy some lunch meat in the United States, you pay a price per pound, but if you want to go to Europe, they're going to sell it by the gram, right? So the units change. So the same thing happens with work. The other thing is force is defined to be mass times acceleration. And that's already in your paper there. Force equals mass times acceleration. F equals ma, you've heard that before. I'll show you where that comes in a little bit. So sometimes to find the force, you might have to take your mass times your acceleration. All right, so we're going to start with the British American system. The unit of force is the pounds. So if I was talking about lifting these two guys here, right, this maybe weighs, I don't know, there's something in there, maybe it weighs half a pound. So that would be its force, where this, I don't know how much it weighs, but it's pretty darn heavy. Maybe 5 pounds. Probably not. Water bottle's kind of thick. We'll measure it later. Maybe 5 pounds. But the pounds is how much it weighs. You kind of think of it like that. That's the force. So I need to do 5 pounds of force to lift that water bottle. The distance, we're always going to be measuring in feet. So even if you're just moving it some inches, you have to convert that into how many feet it is. So the distance is feet. And if work equals force times distance, oh, someone just said it. Who was that? Was that you, Joseph? What did you say?
Foot pounds.
Foot pounds. Oh, I have a big enough box here. I can make it bigger. Move that over. Foot pounds, we call it. Foot pounds. Make that bigger. Abbreviation foot dash LBS. Foot pounds. Foot pounds, that's what we do, that's what we measure work in the American system. So when I say how much work is it to move this 5 pound bottle, if I want to lift it 4 feet, it's going to be 5 times 4, 20 foot pounds. It's a lot of work. Questions on that? That was a little bit straightforward. All right, so in the international system, it's a little bit harder for us because we're not used to the international system. Let's start with any of those units that you might already know. What's the most common, maybe, distance we use?
Meters.
Meters, so it's meters is exactly what we'd expect it to be, so it's meters. And then there's the force for international units. Yeah, he's thinking it's gonna be kilograms, because we either measure things in pounds or kilograms, but here's what's weird. Kilograms are actually not a weight, they're a mass. So a mass is measured in kilograms. The actual force has to be that mass times acceleration.
Newtons.
It's gonna be newtons, some of you know newtons, we're gonna get there in a second. It's called newtons, I'll put it in there now. And let me tell you what newtons are. Newtons is a shorthand for, I'm gonna put it right underneath, kilograms times meters per second squared. Let's talk about why. Force is mass times acceleration. Mass is kilograms. Here's your mass. What is this? What's this measuring?
Acceleration.
Acceleration due to gravity, you guys learned that one in Calc 1, right? Either 9.8 meters per second squared or 32 feet per second squared. So you actually have to multiply by the acceleration due to gravity if you're working in the international system. If you have mass, you have to convert that into newtons. But newtons is just a shorthand way of saying all that. So for example, if I had something that was 5 kilograms, I would have to multiply that by 9.8 meters per second squared. I need someone to multiply that for me, because I can't do that in my head. It's almost 50, not quite. 49 point something, 4? Oh, no, 49.9? 49. Just 49? Oh, that's why I can't hear the point afterward. Just 49, thank you. So that's 49 kilograms meters per second squared, or 49 newtons. So one thing you have to pay attention to is what's your units. If they give you something in pounds, you're set, you've already got force. Quite often they'll give you a mass though in kilograms, and you have to remember to multiply by gravity to turn it into a force. So we got newtons, we got meters, guess what this is? Newton meters, that's true, but it also has a shorthand name. Does anyone know it already? Newton meters, or, have you seen it yet? You're gonna see it soon if you're in physics already.
Capital N with a lowercase n.
Okay, that's an abbreviation, Newton meters. But there's a word.
Joules.
Joules. It's called joules, named after yet another famous physicist. Joules. And we just abbreviate that with a capital J. So most of the time in your international system, it's going to be newtons, and then your work will be in joules. If you call it Newton meters, I'm not going to mark you wrong. And I was talking to Kirk Crowder, I don't know if any of you know him, he teaches the physics, and he was talking to me a couple semesters ago, we were having lunch together. He says, can you please tell your math people to put their units in every single problem? We want the units everywhere. Make sure that we're getting everything multiplied out, so when you get to physics, it's going to totally matter. So you have to remember that newtons is mass times acceleration, and as long as you know the acceleration, which we already knew, that kind of makes sense. And then Newton meters is joules. Okay, on my units, we'll go back to that as we go. Okay, so now everything is simple. I'm in the middle of the page here, if the force is constant, but if not, we have to enter some calculus. But before we do that, let's go down to example 1. That's one of the simple examples. Example 1 says that I am, what am I doing? I want to know how much work I'm lifting a 500-pound iron beam. 500-pound iron beam, 30 feet in the air. And the question is, how much work is that?
$15,000.
15,000 foot-pounds, I heard, because we're just taking the force, 500 pounds, times the distance, 30 feet, and it's 15,000 foot-pounds. Piece of cake. And we'll go back up to the middle of the page, I won't forget, I swear. Example 2 says, now we've got a weightlifter who is lifting a 60 kilogram barbell. It's pretty heavy. 60 kilogram barbell to a height of 2 meters. And the question is, how much work is that?
$1,176 joules.
Okay, how'd you get that?
Multiply 60 by 9.8, then multiply it by 2.
Beautiful. First thing he did was he took his 60 kilograms, recognized that that's a mass, so he multiplied it by 9.8 meters per second squared. This part right here is just the force, mass times acceleration, because of the international system. And then we have to multiply it by the distance. Another color here. So this part was the force. This part's the distance. Tell me again what the number was, Chad?
1,176 joules.
So far, so good. Unfortunately, none of that required calculus, so now you know it's going to get harder from here. All right, so go back up to the middle of the page there where it says everything's simple if it's constant, but if not, we enter calculus. And what we do is we talk about little tiny pieces of work, DW. DW. I'm going to call it a small piece of work. A small piece of work. Because what's going to happen is not everything is a constant weight and you're moving in a constant distance. You'll see that in my first example coming up. So what we do is we take lots of little chunks of work and add them all up. We've seen DW or things with D's before, DX's and DY's, where we were taking small slices or small cylinders, small discs, small washers, and adding them all up. So the DW is just a small little piece of work, and then by integrating that, we then add the total of all of them. So DW is written here as, I lost my place, f of x times dx. Some small little force times a short little distance, right? That's a little short, small force, whatever force times a short little distance. Little tiny chunks. An example will make more sense of that. It's still force times distance though, that hasn't changed. And then if we want the total work over some interval, we would add up all those smaller pieces and end up with something like this. The force times the distance, add them all up from here to there. And my next example will show you how that works. This symbol just means we're adding a bunch of them up. Okay, I think I need to erase all this and do example 3. So example 3 has this chain hanging from a pulley, and I'll tell you why this one's not so easy anymore. So let me erase my table here. Well, you have that in your notes, so we're going to refer back to it as we go through. So example 3 has a 100-foot long chain. Oh, 100-foot chain. It weighs 1,500 pounds. It's a big chain. And it's hanging from a pulley at the top of the building. So I'm going to go ahead and just draw my little pulley here. And here's my chain. Make it kind of thick. There's my chain hanging from the top of my pulley. I'm such an artist. Here's my chain. It's 100 feet long. And it weighs 1,500 pounds. And the question says, find the work required to pull it to the top. So I'm going to start cranking on this little pulley here, and it's going to reel it all up there. How much work is it going to require? So whether I turn that little pulley or if I just stand at the top and pull it, I'm still doing the same amount of work. I'm lifting that chain to the top, right? So it doesn't really matter how it's connected. So the whole point is, we got to find that work. Why is this problem different than what we were just doing with examples 1 and 2. Or is it?
Is it because the work is decreasing as you?
Yeah, the work is decreasing as you pull it up, right? This little piece of the chain near the top, I don't have to pull it very far at all. Maybe it only needs to go up a foot. Where this piece down here has to go all the way up there. And as I pull some of it up, it's getting lighter, right? And so the force is changing as I lift it. Yes.
So would that be, we could use like an integral?
Exactly, so that's exactly where we're gonna end up doing an integral like this. Because it's not the whole chain being lifted the whole distance, we're gonna have to use an integral. If this chain had been lying on the ground, 1,500 pounds all down here, and you wanted me to put the whole thing up 100 feet, then it would have just been 100 times the 1,500. But because it's hanging down, only the top part goes a shorter distance than the bottom, and it gets lighter as we pull it up. So that's where we have to do small little pieces of work. But here's what I like to do. I like to think of the very top of the chain as the origin. So if I'm measuring, I'm going to call this the origin. And then I'm just going to measure down from there some arbitrary distance. Some x, say. X is measuring down. It makes people uncomfortable, but you can put your axes in anything you want. But here's a little slice of the chain right there. Right in there. Take a little slice of the chain. X feet down from the top. So just this little slice needs to be lifted X feet to get to the top. Agree with that? My little green slice has to just go X feet? All right, so the question is, if I just want to lift that slice to the top, what's the force on it and what's the distance? That's the question. Just to lift the little green guy. Let's start with the distance. How far do I need to move him? X, right? That's how far he is from the top. So I got the distance equals X. So the work for him is some force, I'll leave that there for a minute, times X. Force, do we agree that X is the distance? So how much does that little tiny sliver of my chain weigh? What if it was 1 foot of chain? What if I chopped off 1 foot? How much would 1 foot weigh?
15 pounds?
15 pounds, he says. How do you get that?
100 divided by 50.
Yeah, he actually divided this to see how much each foot actually weighs. This actually gives me the density. We can use this to find what we call the density of the chain. The density of the chain weighs 1,500 pounds over 100 feet. So it's 15 pounds per foot. Agree with that? So if I did have a 1 foot slice, it would weigh 15 pounds. But what if it was only 4 inches? That's a third of a foot. It'd be 5, right? What if it's just a tiny fraction? Like a little dx of a foot. How much would that little dx of a foot weigh? Let me just give you some examples. The length of the chain. If I do a little 2 foot length, the force would be what? If it's 2 feet.
100 over 50? Or
30 foot-pounds?
It'd be 30, right? Because it's 15 pounds per foot. So if I have 2 feet, we all agree that'd be 30 pounds? I multiplied by 15. If it was 1 foot, that would be 15 pounds. If it was like half a foot, it'd be 7.5 pounds. Yes, sir?
So would it be like 15 foot-pounds times dx?
Beautiful. If it was dx, it would be 15 pounds times dx. Because what we really did here is 15 times 2, 15 times 1, 15 times a half. If it's really only dx thick, it's 15 times however thick it is. That's the force. So the force in this case is 15 pounds times the thickness, because this little change here, this little thickness of my little green slice, has a little thickness of dx. If it happens to be 6 inches, then it's 1/2 times 15. If it's even smaller, whatever that fraction is, times 15. A fraction of a foot. So you want to remember that dx is a distance. It's how wide it is, right? How thick that little slice is. We agree with Sebastian? Does it make sense? Yeah? So that's my force. So if I put that in there, I have 15 pounds times dx. What is dx measured in, by the way? I want to put my units in here, it'll be prettier. What's dx measured in?
Feet?
Yeah, it's measured in feet. Is feet still part of my units here? Do I need to put feet in there?
No.
Why not? Who said no? Someone said it. Was that you? Go ahead. Why is the feet not there? She said no. I agree with you. I want to talk about our units. Your physics teacher will be happier if you got the units straight. What was the 15? Let's start with the 15. 15 was pounds per foot. 15 pounds per foot. We multiplied by dx feet. That's how wide the little slice was. So what happens? Those cancel out. So it's 15 dx is the pounds. So there's no feet left in there. But this was my force. The distance over here
We'll have feet.
will have feet. I have to lift it a distance of x feet. That's how far we have to lift it. So just that one little green slice has this force, and I have to lift it this many feet. That's just that slice. Yes, sir.
What is dx in this case?
dx is how long this little tiny piece of chain is. So I sliced my chain up into all these little sections. So this one skinny little piece of the chain, how long is it? So, I mean, in real life, if you were chopping it up, maybe it'd be an inch long or something. But in terms of calculus, we're going to slice it thinner and thinner and thinner. So dx is a really infinitesimally small slice of chain. But it's easier to imagine if you think of it being a few inches thick. It'd be that, whatever that number of feet is, times 15.
Is x like the entire distance of the chain, or is that little bit?
X is the piece from here to this particular slice that I drew right here. But I'm going to have to start slicing it. I'm going to have to do a lot of pieces of chain. One second, Jess, if I see you. I'm going to have to do this piece and then do this piece. I'm going to have to keep slicing and add them all up. And X will change every time. So first this is X, and then that's X, and then that's X. And X starts up here and goes all the way down to the bottom.
Okay, makes sense.
Okay, yes, sir.
So in that case, we just plug that direction and put like 0 and then you find the integral for that.
So he says, we just make that an integral now. And say, I want to start slicing this chain up there at 0.
Till you go to 100.
And keep slicing it really, really small until I get all the way down to 100.
Jill,
Yes.
would this be easier if we did this all in Y? In terms of Y?
You can use any variable you want. You can call it Y, you can call it Z, you can call it H, whatever
Because
variable
the
you want.
thickness of the slice is like vertical, so like for me it would just make more sense to call it
You can
Y.
totally do Y. Most people though don't like Y either because it's going down instead of up. So that gets them all confused, but technically it can be any variable you want, so you can do Y. It's all gonna be the same. Questions on those pieces? Of course, then to integrate it, I'm gonna rearrange it so it looks more familiar. So I'm going to still have my 0 to 100. I'm going to have my 15 times my x. I'm going to move the dx all the way to the end here. 15 the x, the dx. I have pounds and feet. So that just tells me my units will be foot-pounds when I'm done. So that was just rearranging these, put them in a different order. Good? Slicing the chain. Wait till you get to the next one where I start slicing some water. I can slice anything. So now we can integrate it. This is actually one that's fairly easy to integrate for once. So that's going to be 15 over 2x squared, evaluated from 0 to 100. 7.5 times 100 squared minus 0. 7, 5, 1, 2, 3, 4. 750? Is that right? I did the math in my head. Someone double checking me?
75,000.
Got an extra 0. Oh yeah, you're right. 75,000. Thank you. So I paused. 75,000. 75,000 foot-pounds. Questions? It's all kind of abstract. We're going to start slicing everything. We've been doing it all semester already. We're slicing up the areas, the volumes, now we're slicing chains, we're gonna slice water here in a second. And it stays put when I slice it too, I don't know how, it's magic. All right there? Okay, so it turns out that I left part of the problem off. So underneath there it says, oh, we forgot to mention, there's a steel beam weighing 500 pounds attached to the end of the cable. So there's this whole big cable that's here, and there's this big old beam at the bottom down here. It weighs 500, did I just say? 500 pounds. He's all the way at the end there.
Couldn't we just take the 75,000 foot-pounds and then add the 500 times 100?
Yes, so there's two ways to do this. So the question is how much work to pull the beam and the chain up to the top. So Joseph says, can't we just take the work for the chain and add on the work for the beam? I think that's fine. I'm going to show you that later. I'm going to show you another way to set it up all in one, because when you do it on WebAssign, there's one of the problems that actually asks you to set it up, and if you set it up separately, it'll get grouchy. So I'll show you both ways. But do we all agree that this 500 pounds has to go the whole distance? It's definitely 500 pounds that has to go 100 feet. So this was for the chain right here, or the cable. I keep calling it a chain. Just the beam, let's squeeze it down here. The beam is 500 pounds, and that entire 500 pounds has to go 100 feet. Agreed? Whole distance. So that is, if I can do it this time, 50,000
Yeah.
foot-pounds? So what's the total amount of work to lift the chain and the beam to the top of the building?
125.
125. This number plus that number. So total work, and I'm going to show you how to set it up all at once. So the total work for both is our 75,000 foot-pounds plus our 50,000 foot-pounds, which is 125,000 foot-pounds. If this problem were on a test, I'm fine if you want to do it in two separate pieces and add them together. So I'm going to show you how you can set it up all at once. Because on a test, I'm not going to say, hey, there's a chain, and then say, oh, by the way, there was another piece. I'll give it to you all at once. So what if the problem had started with, I've got this chain and this beam, how much work to lift it all to the top? So it's not much different, except that when I slice up my chain, there's some other weight on it. So go back to my little green slice of chain over there. If I want to lift this little slice, just that slice, up to the top, this little slice weighed its 15 times dx like we saw before, but it also has this hanging from it. So it's a little bit heavier now. So the force, which before was this, 15 times dx, is now 15 times dx plus 500. Right? There's an extra 500 on there. And we have to lift that for that little dx. It's going to go a little extra 500. So the only thing that's different is you're going to have 15 dx plus 500. Times your, we still have to lift it x. And we still have to go from, I'm losing my place. Oh no, I have this in the wrong spot. Let me take that back. Hang on. Hang on. I just lost my train of thought. I wrote the wrong thing and lost my train of thought. This was originally, trying to match my units, 15 pounds times dx. 15 pounds times dx. And that had to lift x feet. There we go. That's how it was before. But I also now have to take that 500 pounds and lift it a little bit every time I lift a little bit of that slice. I'm gonna pull one little slice up. Every time I take this, every time I pull a little dx up on my chain, we agree this moves dx. And then I pull the next one, it goes another dx. So the distance each time is just 500 times dx. This is force times distance here. This is the original force times distance here. You see that little subtle change there? To make it prettier though, oops, and it was still 0 to 100.
Jill,
Yes,
can we just leave out all the units until the end?
yes. I am fine if you leave out all your units and at the end you tell me it's foot-pounds. Your physics teacher will get grouchy about that. Don't tell him I said yes. I personally do it too, because it's too much to keep track of all of it.
Because technically, like, the 15 is pounds over feet and the dx is feet, and so
Mhm.
I don't wanna, like, write.
That's fine. That's fine. As long as you know what your units are. The main reason that I encourage you to leave units in is when you're setting it up and you're not sure if you have it set up correctly, then you want to check to see if the units all work out the way they should. But if you're convinced that you've got the units right, you don't have to write them till the end. So we have these two different terms here, and all of this, by the way, is with the integral. All of this is inside the integral. Better make that clear. All of that's in the integral. So a shorthand way to write that is this. 15x plus 500 dx. Okay, this is 15 times x, that's just 500. So this is the part that's changing, this is the constant weight on the bottom. So if you're doing this problem on WebAssign and asks you to set it up, this is what it wants to look like. It's the same as what we did with the first part, just add that constant on there at the end. How does that change my integration?
All you're gonna do is add 500x.
All I have to do is add what?
The 500x to what
Add another x over here, right? This is 500x. And we're still evaluating from 0 to 100. So this is the same thing we just did. And this is the other same thing we just did. Right? And that was the first answer for the chain. This was our second answer that we added on to it for just the beam. And it still comes up to be that 125,000 foot-pounds. It's all about little slices and moving little distances. Questions?
I have a question.
Yes.
Okay, so since we're putting units on this stuff, did you want units on the last sections, like when, like unit squared, unit
We're
squared?
finding volume. No, I noticed you put them on there. So yes, so Liba on her homework, we were doing find the volume of a solid. She would write units cubed. But because you're not given units, you could write units cubed. But unless you said this is feet or this is meters, the units don't really need to be there. But if you're given units, then they definitely need to be, because I need to know if you think it's feet or inches or meters or whatever. Okay. How are we feeling about that example? Not gonna kill us? Got 2 thumbs up back there, that's pretty good. Questions? Now she's coming to ask. Okay, let's try the next one. Now we have a cylindrical tank. We know all about cylinders, we've been dealing with them for days now. A cylindrical tank, and it's half filled with water. Get rid of all this. It's half filled with water. We're given it radius and its height, so let me draw the beautiful picture up here. So here's my tank. We know that the height of it is 30 feet. And the radius is, I just lost my place, 10 feet. Radius is 10 feet, 30 feet. It's half filled with water. So here's my water over here. Windy in there, making white caps. Here's my water. How much work is required to pump all the water over the upper rim of the tank? So imagine like there's a little pipe here on the side, and it's pumping the water up and it spills out over the edge somehow. So we have to lift all this water up to the top and then it falls out. Lifting water. So the question says, how much work is required to pump all the water over the upper rim of the tank? And then they gave us some information. Water density is 1,000 kilogram per meters cubed, or 62.4 pounds per cubic foot. So they're giving me the water density. By the way, sometimes you'll see this as a 62.5, not a 62.4. It's given to you slightly different because back in the old days, before we had calculators, the calculations were easier and ended in a 5 than a 4. So sometimes it changes. You're like, wait, I thought it was a 4. I will always give you the density when, on an exam or something where you need to use it. And we'll talk about what that has to do with anything. So, I want to lift the water out of the tank. What do you think I should do first?
Find the volume.
Find the volume, find out how much water is in there. So we could find the total volume of water in there. How could we find the volume of the water?
Find the volume of the cylinder.
Volume of a cylinder, right? So pi r squared times h. How high is the water?
Divided by 2 because it's on the
Halfway,
bottom.
so it's 15. So we could do pi r squared times 15. That's the total volume of the water. We could do that. Do I have to lift all the water the same distance?
You have to move it 15 feet.
All the water has to go 15 feet? That's the problem. So I like the idea of finding all the water. We can find that number. But the problem is we don't have to lift all the water 15 feet. This stuff up here on the top needs to go 15 feet. But what about this water down here on the bottom? It needs to go 30 feet. And there's another piece right here of water that has to go 28 feet. We all see that where the water is has to go different amounts. So now is where I'm going to start slicing the water. Because the water at the top doesn't have to go out as far as the water on the bottom. So of course I can slice water. I need to make up my own rules. So imagine I take a little tiny slice of water with just a little thickness to it. Like a little disc of water. Right? You agree to be a little disc of water? I'm going to do the same thing I did last time. I'm going to let the origin be at the top. Let the origin be at the top. I'm going to call this X. You can call it Y if you want. I'm going to call that X. Just some distance down from the origin, wherever I drew my slice. And then this little thickness to my slice of water, there's a little dx. That's how thick it is. So it's a little short cylinder, short little squatty cylinder. What's the volume of that cylinder? Just a red cylinder of water. The volume of that little red cylinder.
2 pi r dx?
Ooh, you're close. You're thinking distance around the outside. Volume
Oh,
is area times height.
Yeah, pi r.
Pi r squared times dx. Yeah, we're back to discs again, right? So the volume is pi times, what was my radius? And we'll write it first. Pi r squared h in general for a cylinder. Right? In this case, it's pi, the radius was 10. And the height of this little squatty little cylinder is dx. And that's measured in feet. I'm just finding the volume. We're going to talk about why I care about the volume in a minute. But we know how to find volume on the cylinders. Let's do it. We agree that's the volume of just the red cylinder, the little short one? A disc of water. I deliberately put the units in here. So I'm going to end up with 10 squared, so that's pi times 100 dx. And I have feet. Feet. Cubed, right? Because feet squared times another feet over here. Cubic feet. That's how many cubic feet of water are in the little red slice. Why do I care about that? Chad had a great idea. Let's find the volume. So I found the volume. How does that help me?
That's what you would plug in for if you were doing
You couldn't hear.
it. That's what you would plug in for if you were doing it in the room.
We're going to need to plug it in, but I need force times distance. That's a volume,
Oh.
right? But I claim it's going to help me get one of those two. Am I in the international or the American system? American system, I'm seeing feet and pounds, right? They gave me all this information, but they gave me more than I needed. But because this is all measured in feet, I know I'm dealing with this. What does that density tell me?
Because you can go from feet to pounds.
Perfect. This tells me how to go from cubic feet into pounds. This tells me each cubic foot weighs 62.4 pounds. So if I have this many cubic feet, I can now get the force. The force is going to be the volume times the density. It's going to be pi times 100 times dx cubic feet, there's my volume, times my density, 62.4 pounds per cubic foot. Deliberately putting my units this time so that we can see how it's going to give us our force. So I personally don't have it memorized, I need to take volume times density. I realize I have to, but the reason I know I have to take volume times density is I need my units to work out. I need something to cancel out my cubic feet. So if I have cubic feet here, that's going to reduce the cubic feet here. My answer will be in pounds. So I will have the force just for that little slice. So now we have 6240 times pi times dx pounds. Agreed? Multiply it in my head again. Now remember the question was, I didn't write the question down. The question is how much work to pump all that water out. So far what we've done is we've taken one little slice and figured out what the force is for that slice. So to make it work, I need to take the force and do what with it? Multiply by distance. So I need to take that force times distance. So work equals that force, which is now over there, 6240 pi times dx pounds, that's my force, times my distance. How far do I have to lift that slice of water? X, right, because I measured from the top there, it's x. So times x, which is measured in feet. Notice that we now have foot-pounds, which is what we wanted. And then I'm going to have to slice the water. Be careful. Slice the water from where to where? Remember, zero's at the top, and I'm measuring going down. 15 to 30, right? There's no water up here for me to slice. When I'm at 0, there's no water. I'm not slicing water at 1, at 2, at 3, at 4. But when x gets down to 15, that's when I'm gonna start slicing. I'm gonna slice it from 15 all the way down till I get to 30. 15, 16, see that? So it's not always just 0 to wherever. 15 to 30. There's the setup for that. And I actually will take my pencil or my pen and start doing exactly that. 0, nope, there's no water yet. Where do I hit the water? Oh, at 15 I hit the water because it was half filled. So I would slice it from 15 and keep slicing the water to the bottom. If you had said 0 to 15, that would have been if it was only filled from the top and there was nothing down here and you were lifting that stuff out, lifting that air out. All the same. We work this one out, see what we get? Some big old number. We can do it. I'm going to pull out the units, I'm going to pull out my constants out front. 6240 pi, integral from 15 to 30 of x dx. And my answer will be in foot-pounds when I'm done. Which is x squared over 2. 6240 pi times x squared over 2, evaluated from 15 to 30. Some busy work now. Plug in your 30, plug in your 15, let's see if I have an answer here, we'll compare notes. I have a huge number of foot-pounds. See if I can write it in here. 2106,000 pi. Anybody already worked it out while I was yapping? That 2 and 1 just ran together, let's make it prettier. It could be wrong, don't trust me. Anybody calculating it? Waiting for a confirmation or someone to argue with me? I left the pi there, I didn't multiply that, I just left it there. 2106,000, that's what I got. Chad agrees with me? Can I have one more person? Don't disagree with me because I asked, so I want you to actually agree with me. I want your calculator to agree with that.
Yeah, I got the same.
You got the same thing too? Okay, good. I don't always trust my notes. I'll scribble, I'll do something at midnight and not pay attention to my details, and then I get to class, oh look, I made a mistake. I'm human too. Very few problems in a lot of time just now. Ready for a break? Okay, let's take a break. I'm going to make some copies real quick. I will pass back some other things, and then we'll do a little bit more work. We'll work with some springs after that. Let's get back to work. That's a math joke. You get it? She laughs at me. Thank you. We're getting back to work. Literally. Yeah. Oh, thank you. I needed that too.
Mrs. Sutherland?
Yes, sir.
So, I had a question about the labs and how you grade it.
Yes.
So we do everything in the middle of grade 6-1?
Yes.
Okay, sorry. Okay.
Yeah, I grade about half of them,
I just
sometimes a
wanna
little
make sure,
more.
'cause my last semester you did that as well, so I want to make sure.
Yeah, and you'll notice I circle the ones that I grade. So if I graded, number 1A and 3B and whatever, I circle the ones I graded so you'll know which ones you do have feedback from me on.
Okay,
And so I just grade those.
thank you.
If I had to do all of them, you would never get your papers back because I would be grading nonstop. I have to sleep at some point.
I like the way Crowder grades, he just assumes that if we did it all together, it's all right, so just.
The Math 60 is the details are really kind of crucial on how you get there, so I'm always looking at all the details. Look at it. But you'll be thankful when it comes to a test that you have all the details right. You will be, that's the point. Okay, we're moving on to Hooke's Law, page 19. Still working with work. Hooke's Law is a very specific case of work dealing with springs. Dealing with springs, we're on page 19 of the notes. There's beautiful pictures. Here's my picture of a spring, and here's the same spring stretched out. I'm such an artist. So Hooke has this law named after him. He's the one who figured out that the force required to either stretch a spring or compress a spring is directly proportional to how far you're stretching it. I don't know how familiar you all are with springs. Some of us played with slinkies when we were little, back before we had electronics. And some of you still know what a slinky is. Now slinkies are springs with that are really easy to pull and push. They practically fall apart on their own, right? There's no tension really needed. I suppose if you wanted to make it perfectly straight, that would require a lot of force. But you can open and close a slinky, no problem. Anyone ever have a garage door spring break? Yeah, you know what that's like? Oh, those things have so much tension on them, they snap. Luckily they're on rods that are supposed to connect them, but someone could get killed by a garage door spring. They are so, you can't physically, a person cannot stretch them or compress them. You can put some force on them with the way the garage door opener works and all that, but those things are like solid. If I wanted to try to make a move, I'd be out of luck. So every spring has its own constant for how much force is required to either stretch it or compress it. And whether you're pushing a spring in or pulling it out, it's the same amount of force. It just matters on how far you're pushing it or pulling it. And it's all defined to be how much force is required to pull it a certain distance from its natural length. So its natural length was just sitting there by itself and no one's pushing or pulling on it. How long is it? And so once you move it from its natural length, every time you move it a little bit further, it multiplies that by the force. So down there about halfway through the page there, it says Hooke's law. The force F of x required to stretch it x units beyond its natural length is F of x equals kx. That's the force every time you're working with a spring. This is Hooke's law. Most important thing is this is called the spring constant. That's not the most important part. That's what I was referring to, saying that every spring has a different amount of force you need to push it or pull it, depending on what it's made out of, how thick it is, and so forth. So every spring has its own constant. And x is always the distance from its natural length. Oops, natural length has another L in it. Someday I'm going to get a bunch of springs to bring in the class. But imagine I have a spring that's like, this long. It's pretty thick. And I could maybe pull it a little bit and get it to start to stretch. I'm maybe strong enough to just stretch it a little bit, maybe an inch. I could get it to go an inch. But if I want to go another inch, I have to be a heck of a lot more stronger to go further out. And the further I go, the harder I'm going to have to pull. It's not like it's just constant force to open it and close it. Every time you go further out, it gets harder. That's what this is saying. There's some x, however far out you go, the force gets larger by multiplying by whatever k is in that case. So every spring has a constant, and then the force changes all the time based on how far you stretch it or compress it. Doesn't matter either way. So let's look at example 5. On the bottom of the page, we have a spring with a natural length of 20 centimeters. Lost my place. There we go. 20 centimeters is the natural length. And a force of 25 newtons keeps it stretched to 30 centimeters. Whoops, 30 centimeters. So if I was just leaving it alone, it would be 20 centimeters, but I can apply 25 newtons of force to get it to go to 30. That's the beginning part of example 5. And the first question says, how much work is needed to stretch it from 20 to 25? Part A. Work to stretch from, now you have them written in front of you, but I want people in the video to know the question. Work to stretch from 20 to 25. So I'm given this information about the spring, and then I'm asked for a question about it, how to find some work over there. The first thing you always want to do before you try to answer the questions is find K for this particular spring. every spring has a K, a constant, we need to find K for this spring. So the first step, before I even bother with that question, I don't care about that question yet, find K first. This f of x, remember, is the force. So what should I do?
Multiply the force by delta x of the original equation.
We don't have a delta x yet. We're going to need that to find work. So you might be ahead of me maybe, but we're just trying to find k. Find out what this k is for this one. So there's no delta x quite yet. Yeah,
Here's
Ken?
the original information that they give you to find K. 25 newtons is equal to K times the difference between 30 and 20. which is
So he says use this information and plug it in up there. 25 newtons is the force. That's the force. And this 20 centimeters is, oops, that's the original one. Sorry, that's not it. This 20 centimeters is the natural length. The fact that I'm going to 30 is telling me something here,
That
right? What's it telling me?
it takes 25 newtons to stretch it 10 centimeters.
Aha, so that's the delta x you're
That's-
referring
yeah.
to. So this right here means x equals 10 centimeters. Why? Why is it 10?
It's going from 20.
Yeah, Mike?
Should we convert centimeters to meters?
Definitely. I'm so glad you saw that. Did you guys all hear his question?
Yeah.
We better convert the centimeters to the meters or the whole thing's not going to work. I'll do that in a second after I'm done organizing it, but you're right. Anytime you recognize which system you're in, either everything's in feet and pounds or everything's in kilograms and meters. So we're going to change the meters here in a second. What about the 10? Where'd the 10 come from? Yeah, Sebastian?
Because it's 20 centimeters as natural length and you're stretching from 30 centimeters.
Right, I can't stress that enough. X is always the distance you've changed it from its natural length. It was 20, we stretched it to 30, so we stretched it 10. Okay, so we have that. Let's convert that into meters right now. Converting into meters, we're going to divide by 100 and multiply the decimal over 2 places, whichever one. So that's 0.10 meters. Has to be in meters if you're in the international system. I already have newtons and I have meters. So let's figure out what K is. So in this particular problem, my force was 25 newtons. I don't know what K is. My X we just said was 0.10 meters. Solve for K. K equals 25 newtons over 0.10 meters. K equals 250? I'm dividing in my head.
Yes.
Yeah, thank you. Yes, there are units. You could call it newtons over meters. Because newtons have meters in it, it's like kilograms, meters, or kilograms per second squared. I'm not worried about the units for K, but if you want them, you can carry them around. They do have units. That is my spring constant. So now that I have K, I know that for this particular spring, I know the force function is this. This is the force function. I haven't even tried to answer the question yet. Make sure you find K before you try to answer the question because of this is some different information over here. Okay there? Now that we have the force function, we can find the work. So, we're going to find work by doing what? Force times distance, right here on top of the board. Force times distance, we just found the force. What do you think the distance is going to be?
Times
0.5 meters.
0.5, 0.05 I think, yeah.
Or
To go from
0.05,
20
yeah.
to 25? 20 to 25, I agree that's 0.05. But I am not stretching the whole spring 0.05. Let me tell you what I mean by that. I'll go back to my beautiful pictures over here. So let's say that this one is 20 and this one's 25. I agree my scale is off, right? So this is that extra 5 right here. So this end of the spring has to go out a whole 5 centimeters, right? But like this little piece right here, it doesn't go 5 centimeters. It's gotta get stretched a little bit less than that, right? Because it's getting stretched out. So it's not that the whole spring is going 5 centimeters. The tip of it is, but the rest of it's kind of proportionally getting spread out there. So again, it's like we're slicing a little spring and moving each little piece a little bit. So each little tiny piece of the spring is gonna have to get stretched out some distance. And that little distance, a little short little distance, dx. So the distance is going to be dx in this case. The force in this problem is going to be 250x. I lost my place already. So dx is just some short little distance for each little part of the spring, because each little piece gets moved out a different amount. And then, what are the x values? How far am I moving it from its natural length? I'm going from 20 to 25. How far is this from its natural length? 0. Right? That's not any distance away from the natural length. That is the natural length. So this is x equals 0. Right? That's nowhere from its natural length. And then I'm going to keep stretching it till I get to 5 centimeters, which is 0.05 meters. Always, I can't say it enough, I'm going to say it and you're going to still make this mistake, from the natural length. So I'm going from its natural length to 5 centimeters past its natural length. So there we go. These are like some of the easiest integrals. 0 to 0.05. What are my units going to be for my answer? Joules? We sure? Why isn't it foot-pounds? International, right? We got newtons times meters. Newtons, right? Times meters. This is newtons, this is meters. So my answer is going to be in joules. When we integrate this, I'm going to divide by 2 as I integrate. That's 250 over 2. Okay. X squared. Evaluated from 0 to 0.05. So the calculator want to help me out there? I set it up, but I didn't work that one out. 0.31. 0.3125
Yeah,
joules.
so do you want us to round out all the way, or will you tell us like how many you want us to go out?
Well, this was an exact answer, I think, right? Just
Yeah.
keep going. If it's an exact answer, just give me the whole thing.
Right.
If it needs to be rounded, then if my directions don't say, I'm not that grouchy about it, but usually, like, you know how the other one earlier, I left the pi in there, like leave the pi, and it's exact. This one is exact. So 0.3 joules to stretch it from 20 to 25. Questions on that? I'm going to ask you to set up the next one, so make sure you ask me a question. Okay, try to set up the next one, which goes from, what did it say, 25 to 30. So part B wants to know the work from 25 to 30. See what answer you get compared to the other one. Try that, see what happens.
Jill,
Yes,
is this assuming that 25 is the natural length, or is it from the previous question?
it's still the same spring that we talked about here. So this original part described the spring. Now that we're still dealing with this spring, so the K is still 250, what how much work to start at 25 and go to 30 with the same spring. It'll always be the original spring, otherwise they'll tell you something else. If you tell you it's a new one. So I think I checked everybody's. If I missed you, I'm sorry. Clear? Did we have these bounds? Yeah, of course we did. Maybe we got there eventually. It's the same spring, so the force hasn't changed. The only thing that changed is that the bounds are different here. And when you calculated that, it was 0.9375.
7.5.
Thank you. Jules? So notice what happens here. In this first part of the problem, we stretched the spring 5 centimeters, right? From 20 to 25, it was 5 centimeters, it was 0.3-ish joules. This was another 5 centimeters. 3 times as much work. Right, this number is 3 times as much as that number. So to do it the first little bit, it takes a certain amount of work, but then to go the same distance again, it's triple the work. Because those springs get harder and harder and harder to pull the further you get out. Spring problems are some of people's favorites because they're all the same. They're all kind of straightforward. If you can find K and you can find your X's, they all kind of start to look the same. There's one exception to that, and it's on your lab assignment, and I'm going to point to it now so that you can find it when you get to there. Flip over to page 21, and page 21, number 2. On the lab for this section, page 21, number 2. This is the section we're on right now. 6.4 lab. I think I'd have them memorized by now. You even said it back then. I'm not going to do the whole problem, but I want to help you see what the problem is giving you. It's different than what we just did. So it says that the work required to stretch a spring 1 foot beyond its natural length is 12 foot-pounds. How much work is needed to stretch it 9 inches beyond its natural length? Not much information there. To go 1 foot past the natural length. Takes, where'd it go, 12 foot-pounds. And then it's going to ask a question about the 9 inches. But remember, the question I don't care about yet until I do what? Find K, thank you. I'm going to find the K and then worry about the question that has to do with the 9 inches. The 9 inches I can't do until I know what K is for this spring. It's a different spring. How is this question different than the one we just did? In terms of what you're given.
That one's international.
Okay, one's international versus American, so I agree that's a difference.
We don't know the natural length.
We don't know the natural length, that's another difference. There's something even bigger difference than those, so I'm glad you guys are thinking those are 2 differences.
We don't know the force.
We don't know the force. In this problem that we just did, they told us the force to go 0.10 meters, right? We were able to plug in the force equal to K times the distance and solve for K. We had a force. We don't have a force over there. How can I do this step? Force equals K times, if I don't have the force, right? What do we have instead?
The work equation.
We have the work. How do we get work? Force times distance, and in this case of a spring, we have to do this integral to get the work. So we have this is X, no problem. We got the X, it's 1 foot past its natural length. But this right here is work. It's not force. But in general, to find work, we integrate the force function from wherever we're going to wherever we're stopping. The difference here is we don't know what K is. So we're gonna still set it up though. Whatever my Kx is, I'm going to integrate it from where to where?
0 to 1.
0 to 1, thank you, because it said from its natural length to 1 foot beyond its natural length. This is the work to do what they're talking about here, right? 1 foot past its natural length. And if I do this integral, what should it equal? 12. That's the only hint I'm going to give you. You're going to need to solve this for K. Solve this for K. And then you can answer the question. How are we going to solve it for K?
K is a constant.
K is a constant. Okay, I like that. Then what? What are we going to do? K is a constant.
Force by distance.
Well, the distance is in there, that's the dx is in there. So how can I solve this equation to find out what K is?
Divide by x.
I can't divide by x because x is in the middle of an integral, unfortunately. What were you thinking?
So can we move, since it's a constant, can we move K from there and then do the antiderivative of that?
So she says it's just a constant, pull it out front. And then you can evaluate that integral, right? You can evaluate x, the integral of x. Please tell me yes to that question.
Sure.
You know that? Sure. I almost believe you. You can integrate x, evaluate it from 0 to 1. That'll be multiplied by k. Then you can solve and set that equal to 12. Okay, I'm gonna let you guys finish that one. I just wanted to point out that almost every other spring problem is going to look like this one. And then every once in a while, they throw another one in where they're giving you work and not force. So don't assume that you have force. Read the problem carefully. Questions about work? You think we're good? So here's the good news then. Good news if we're done. No questions? There's only 4 lab problems too. I don't think that's very fair to me at all. There should have been a lot more. I think I'm going to grade them all, by the way. There's only 4. So what we're going to do now is move on to 6.5. We may or may not finish it in the next 20 minutes. It's that short. If you looked at our schedule that I gave you on the first day, we're starting 6.5 today and finishing it next time if we don't get through with it. 6.5 is probably the easiest section we'll do all semester. Yes?
No, I mean like 6.5 lab assignment to be due next week is the week after.
It is due, I'm trying to look to see when it's due. It's due, yeah, on the 19th.
Okay,
Right, so it's never due until the next week after I've worked on it.
fine.
Well, yeah, the next week, yeah, so because they're all due on Tuesdays. A few exceptions are when there's an exam and the schedule's off. On the last page of the first day handout I gave you, there was this little schedule here. So that always kind of gives you a heads up on what we're doing. Mine's white, and yours was yellow, maybe? Tells you what we're doing any given day. And you can always tell what's due also by looking on Canvas. Has all the dates on there. Okay, the easiest section, since we did one of the harder ones. Easiest one, the average value of the function. So let's talk about what the average value of a function even means. And what do you guys know about an average? Like if I wanted to find the average age in this classroom.
Add it all up, divided by.
Add them all up, divide by, let's say there's 30 of you in here, and add up all your ages, divide by 30, that'd give me the average. Right? Well, what if I had 1 million people? Same thing, just take me longer, right? Add up 1 million ages, divide by 1 million. What if I have an infinite number? Oh, it must be an integral, he says. So imagine this function that you have. I'm on page 23. Average value of a function. These are quick and straightforward, I think. Page 23. So here's a rough rough sketch of this. This is at 6, like 12. What picture do you have on your notes there? I want to know what the average Y value is in this picture. The average Y value. How high up do they go? I didn't label the Y axis. It's like it goes up almost somewhere between 10 and 15. I can't really tell what the highest one. The highest one looks to me like maybe 13-ish or 14-ish. I can't tell for sure. Roughly. How many Y values are in this graph? A lot. Can you be more specific? Infinite number, right? I mean, here's a Y value of 0. Here's a Y value of, I don't know, roughly -2 maybe. I can't tell, my scale's not so great. Here's another Y value of negative, and here's a couple other ones in between. And every time I think I have another Y value, there's another one next to it. So do you all agree that I can't add them all up and divide by infinity? Don't have enough time for that. But that's the whole idea, is what is the average Y value? How do you find it if you have an infinite number? So the visual that I have there is, imagine if you had this total area here, this total area here, area under the curve. Does it stop right on 24? I put my notes down.
Yeah.
Okay, good, thank you. And remember back in Calc 1, you learned this is some positive area. This is like a negative area because it was below the x-axis. So we could estimate what that total area is. And then the idea of the average value of the function is, what if you took that total area under the curve and spread it all out evenly? So to make a nice big chunk, a big rectangle that was all nice and solid. So instead of adding them all up and dividing by infinity, we're saying take the area that's all free-formed and make it uniform. That's what we mean by the average value. So if I take all that green area right there, I'll make sure I do this similar to what I have. This looks like it's a little bit below 5. It says take that all and kind of restructure it and put it in here. And if we take all that green area and then just kind of smash it all down to fit it into a rectangle, it would fit into, say, that rectangle. We agree if we could push, slice and water, now I'm pushing curves around into rectangles. That's the idea visually. This Y value right here is what we call F sub AVE. People call it phase, but it's F average. Yes, sir?
So right here it's labeled T average, doesn't matter which one it is.
I didn't hear what you said. Can you say it again?
It says it's labeled T average on the graph, doesn't matter which one
Oh,
it is.
yeah, that's interesting. I didn't even see that on the graph. It is labeled T average because it's probably, it was a temperature graph to begin with. You see the Y-axis has a T on it.
Yeah.
I didn't even notice that, so that's why they
So
called
it
it
doesn't
T
matter,
average.
as long as it's
Whatever your
below.
function is, it's the average. This one was measuring the temperature and I already had forgotten. If you look on the definition right next to it, it calls it F average. But basically, whatever your function is measuring, it's the average. Y value, T value, whatever the variable might be. But the point is, what is that number that spreads it out evenly? That's the idea. Okay, let me ask you a question. If this number right here is F average, what's the area of my red rectangle? What's the area of my red rectangle? Length times width, someone just said. Oh, well, how far is that? So the red rectangle is 24 by... That's F average times 24, right? Length times width? I don't know what that average number is. It looks like a 4 point something to me. You guys all agree with that? The red rectangle, length times width, F average times 24? What's the area of the green part? The green area. What symbols can I write to find that area under a curve? The integral from 0 to 24 of whatever my function is, dx. That's the area under a curve. That's the green area, that's the red area. And what did I tell you has to be true about those two things? I want them to be equal. Right? That's the whole point. I want the red one to be the same as the green one. So that means that the average value times 24 has to equal the integral. Ooh, I heard you whispering there behind me, I like it. And he's over here going, divide by 24. So we're going to divide by 24, then we can solve for f average. So f average is 1/24 of that integral. If I want to know what that number actually is, what is the average value of that function, I just have to take 1/24 of that integral. Which is where this formula comes from. I much prefer talking about that first than just looking at the formula going, why, what is that? Oops, erase that. So then there's the formula that tells you how to find the average value of the function. That looks exactly like this. F average equals 1 over b minus a times the integral from a to b f of x dx. What were the a and the b in that first example? What were a and b? Over there. 0 to 24, right? We went from 0 to 24, which is where these bounds came from. And guess what 24 minus 0 is? 24. So when you're asked to find the average value of a function, really all you need to do is take the integral over your integral over your interval, if I can speak, and divide by the length of that interval. Take your integral and divide by the width, I guess. The width of your integral. So let's do example 1. We'll do the other one next time, I think. Example 1. Find the average value of this function, x squared. This is a good one for those of us who have to practice our u substitution. And the other two. Find the average value of this function on that interval. Okay, I'll see where I am, example 1 there. What should I do? Yes, sir.
You're gonna, do the F average is equal to, and then 1 over BA, which is number 2.
1 over, I'm going to actually write it out, 2 minus 0, right? This would be minus a, times the integral from 0 to 2, x squared, 1 plus x cubed dx. It's really a review problem. That's 1/2. Now here is another review problem. For those of you who don't remember your u substitution as well as others, now's a good time to ask questions. But the question I have for those of you who do remember it is, why is this an obvious, Jill's calling it obvious, an obvious problem for u substitution? Why is it obvious?
The function within a or a variable within a I don't remember. Never mind.
That's okay, no, you were halfway there. Because you've got this function, 1 plus x cubed, inside another function, that's what makes it a candidate for u substitution. But not always a good candidate, which we're going to learn in chapter 7 next week. But because you have a function inside this other function, that means u substitution should be my first thought. But there's something else that makes it a good candidate that clarifies that u substitution will work. So those of you who think you're a little more up on your u substitution, try to answer that for me. How does this look? Was that you, Mike?
Yeah.
What's that?
You got the derivative of the bigger inner function on the outside, and that's how you know it'll work.
Perfect. So he said you have the derivative of the inner function on the outside, and that's what tells you it works. So you guys are both on the right track. 1 plus x cubed is inside another function. So call this the inner function. It's stuck inside that square root. I wish it wasn't. What's the derivative of 1 plus x cubed? 3x squared, right? There's an x squared in it. There's an x squared hanging around out here. That's what tells you it's a perfect candidate for u substitution. So it's actually both. You have to have an inside function, and you have to see its derivative hanging around somewhere. There's a few exceptions to that derivative hanging around thing, but that's always a good sign that u substitution will work. When we start going through a whole bunch of other techniques of integration next week, I'll keep mentioning that, oh, I don't see its derivative hanging around, or I do see its derivative hanging around. But the derivative of this has an x squared, and I see one hanging around. So I'm going to do a u substitution. I love the way you said that. So the u is usually your inside function. You then take the derivative of that to find your du, 3x squared dx. This is the part where we now know it's a good idea to use u sub. Sometimes you can't see it. You can at least write this down. I see the x squared in there. Now, depending on who taught you your Calc 1, your next step might look similar to mine. It might be the order that you simplify might be different. I like to simplify for what's left in here. I see an x squared and a dx right there. This part I can see is going to be a square root of u. That part's no problem, right? But I see the x squared dx. I like to solve this for x squared dx. There's other ways to do it. If you like your other way, I know what you're doing and it works too. That's 1/3 du. X squared dx equals 1/3 du. I just divided both sides by 3 right here. So that means I've got 1/2. I have the square root of u. But these two guys right here, x squared dx, become 1/3 du. Right? What was underlined over there is now this part. Different ways you might have gotten there. Notice I didn't put 0 and 2 in there for my bounds. Crucial that you don't put 0 and 2 in there. I'll mark you wrong. These are not 0 and 2. These right here, because this is a dx, these are x values. This is x equals 0 and x equals 2. Because this says dx right there. So this now says du. So these need to be u values. This needs to be u equals and u equals
91.
Keep going. What are you saying?
Is it u equals 9 and then at the bottom 1 or not?
Yes, it is. I'd look at it. That's why, was that your hand, Evelyn?
Yeah, no, he already said it.
Oh, you were going to give the same answer? So how'd they get, they said 1 and 9.
Plug those x values in the right function.
Plug these x values into this u function to find out what u is. So for x equals 0, then u equals 1 plus 0 cubed, so that's 1. And for x equals 2, u equals 1 plus 2 cubed, which is 9. If you write 0 and 2, it will be wrong. Because you plug 0 and 2 in there, that's very different than plugging in 1 and 9. Make sure your values for your bounds match your variable here, which is why it matters that you write dx or du or dy or whatever it might be. I'm going to simplify by bringing this 1/3 out front now too, the constant. 1/6, the integral from 1 to 9. I'm going to rewrite this with a fractional exponent so I can integrate it better. One sixth times 2/3 u to the 3/2. Evaluated from 1 to 9. You guys okay where the 2/3 came from? Yeah? So that simplifies into 1/9. And then I have 9 to the 3 halves minus 1 to the 3 halves. The 1/9 came from multiplying these. I don't know what that noise was. I think we talked on day 1 about how to simplify those fractional exponents. You can use your calculator, I know, but I promise you can do it without your calculator. What does this mean? What's it telling me to do? Take a square root and then cube it, right? Take the square root of 9 and then cube it. What's the square root of 9? 3. 3 cubed? Look at you guys doing it without your calculator. That's impressive. So 1/9, 27. This means square root of 1, which is 1, and 1 cubed, still 1. The answer is 26/9. It's the average value of that function on that interval. Now, for those of you who do love your calculators, one thing I recommend is actually graphing this on your calculator and zooming in just between 0 and 2 to see if the average value looks to be about, I don't know, it's almost 3, a little bit below 3. Because otherwise, if it doesn't look to be anywhere in that window, something might be wrong. Yes, sir?
So do we have to choose our balance for you? Can we just plug into the original equation?
If you plug in 0 and 2, you're gonna get a different
No,
answer.
no, not the balance. So, because you know how like 1 cubed back here?
Oh, this is a good question. So Daniel was asking if he doesn't want to change the bounds, but he wants to integrate and then put the x's back in after he's done. That's okay. The problem is how you notate that is really not a way to do it. Some people just like leave this off and leave this off, and then once you get to here, they put it back in and put the bounds back on, which will work if you do it right, but in between, it's not exactly true, is the problem. So you don't have to, but just make sure you make a note that I'm changing back to X later or something so I can follow it. Because this is a definite integral, they're asking something here. So I'm following what you're asking, just make sure that what you write is mathematically correct. Yeah, worry about it. If you're making a little note like side work, I'm okay with that. Okay, so we'll finish this one next time, and we'll start chapter 7. Join the lab if you want to come join me.